Thank you for joining us today. This is going to be a short webinar on Solidworks flow simulation and routing. I'm Mitchell Henry. I'm an application engineer here at Concepts in Production, and I'm one of our two flow simulation specialists. We're going to follow today a quick little demonstration of a heat exchanger problem. As you see here on the screen, we've got a simple copper tube heat exchanger. We're going to be trying to cool some water that starts out 150 degrees, and we're going to try to get it below 100 degrees. Our pipe diameter is just a 1/4 inch, and what we're cooling it with is air flowing over it at 35 degrees Fahrenheit, and we have a flow rate for both our air and water. So here I'm going to start it out as a assembly because I'm going to put together multiple parts to create our model. Before I get into actually creating any parts, I'm going to create a layout of what our pipe looks like, just as a assembly level sketch. So I'm going to just do this short little bend. So here's the basic shape of what our heat exchanger is going to be. I'm going to step over to the design library. I'm going to grab the routing file. Let me step there so I can show you. So we're going to grab the routing folder. Today we're going to be using tubing, and I'm going to grab a tube fitting. Now the tube fitting is a simple part. We're going to grab the 25 NPT brass fitting. So the nice thing of starting with one of these fittings is that it's going to automatically know what type of tubing it needs to have associated with it. And it's going to try to start routing as soon as I drop it, but I'm going to tell it no, because I'm going to orientate our part first. Now this one came in free floating, which is good. So first off, I'm going to do my basic mating to put my parts in their correct locations. Just a few little concentric mates and coincidence mates, just to match them up and put them in their correct spots. Now, here in a second, I'm going to start the actual routing, and I'm going to do that by turning on here the visualization. I'm going to go down to this icon is the routing points, and that's going to show me both the connection points and the relay points for routing. You'll see here I have a relay point there, and this one is not visualizing. There's a connection point, which is what I lined up at the end of our point. If I step into the actual fitting features, we see at the bottom there's the relay point and the connection point. The relay point is a route can pass through that point, but a connection point is like an end point. Now that we can visualize the connection points, I'm going to step over to the routing toolbar. Here's the magic of routing is I can just select this connection point, and I'm going to click Start at Point. And here it's going to ask me, hey, is this the pipe setup? So yeah, 1/4 inch tube. The only change I'm going to make is I'm going to change the bend radius from 1/4 inch to 3/4 inch. And see here, it's already starting to create the route geometry for us. And this is just a visualization. So I'm going to put this point on that point. Then I'm going to go up and I'm going to grab the tubing specific line. I'm not going to grab this from sketching, just that I don't have any issues. And see there, when I put that second line, it auto bends it for me. I'm going to put the other end there on our endpoint, and see there's our fully defined route. Granted, this is a simple one just to demonstrate, but you could do much more complex. You can do it with a spline in case it's like a wiring, so it's a little more bendy. But here we easily just created our route or our copper tubing. I'm going to turn off those connection points and our sketches because we don't need to visualize those anymore. And it's going to auto create a subassembly for it with a routes parts folder. I'm going to go in here and take our route tube, and I'm actually going to change the material of it to our copper. Here we have our heat exchanger, really quick, really easy construction of it. But for the flow simulation, I'm going to simplify it some. And if you have any experience with CFD or FEA styled simulations, you'll know that simplifying the model can often drastically reduce the simulation time required to calculate it. So I'm just going to create a configuration over here called Simplified Simulation. And that way I can go over here and create a much more simplified version of our heat exchanger. The first step that I'm going to do, I'm going to get a section plane, and I'm going to put a sensor, just a simple geometry that I can use to select a face of a little coin-shaped tablet right there. So I'm going to add in a new part for this. I'm going to edit said part in the assembly, and I'm just going to put a plane right there, right at the entrance to the fitting. And I'm going to use convert entities to make this a little easier on me. I'm just going to grab there and grab a circle there. And you see it grabbed two circles, converted them. I'm going to just create an extrusion of that. And now we've got simple little tablets, essentially, that the water is going to flow by. And when we get to the simulation, we can actually turn the simulation to ignore these so that they don't actually interact with the study, which is good. So we see those. We also need to make the inner part of the tube watertight from the surrounding. So I'm going to step over to the flow simulation toolbar, and I'm going to use this button, the create lids, and this is going to let me select any surface, and it's going to auto create a little disk for me with any closed interior contours within that surface. That way we now have a watertight or airtight inner chamber of what our tube actually has. Now I'm going to put in one more little sensor part. I'm going to put a plate behind it, behind the whole array that we can apply a sensor to so we can see the air flowing over the part. I'm going to once again edit this part in context of the assembly. And I'm going to, on that part, on its front plane, I'm going to create just a simple box. And then I just have to define the size of it. Jump in and do that real quick. 11 by 3. And our offsets are 0.5. I'm actually going to make this a little larger. So here I'm going to make sure that it's at least as large as our entire part. And that was just creating a sketch. So I'm then going to create geometry from this sketch. I exit out of editing it, so I'm going to go back to editing it. I'm going to select that sketch. I'm going to do a extruded boss feature, but I want it to be behind it instead of in the middle, so I'm going to do an offset. I'm going to offset it 1/2 inch behind it. So we see here, now we've got our plate halfway behind. Our lids are closing off the pipe, and inside we have our little sensor tablets. One last thing I'm going to do is I'm going to suppress these two features because I don't actually need to see the... I'm actually going to refine our shape here. There we go. I applied a few things to the incorrect surfaces. Give me a second to catch up on them. I'm actually going to just delete these and recreate new lids. So our flow simulation, once again, I'm going to grab the lid tool, and I'm going to put a lid on this surface and that surface. So here, now we have our simplified version of our heat exchanger for the flow simulation. I'm actually going to make that transparent, just so we can remember that that's not going to truly exist in the study. Now I'm going to leave most of the study, the flow simulation study creation, in this section view just because it's a little easier to work with. I'm going to make this one transparent as well so we remember that that's not supposed to exist in the study. So here we've prepped our model. Because we've set up the configurations, I can quickly step between the configurations of what the heat exchanger is really like and what the simplified version should be. And now I'm going to go set up our simulation. So under the flow simulation tab, the first step we're going to do is we're going to set up the wizard. And the wizard helps us grab all the little details of our simulation in general. So I'm going to call it heat exchanger using the current configuration. Next, we're going to grab our unit system. I'm going to switch to the inch-pound system. Here's where we start to get into the actual simulation. This is going to have external air flowing over the pipe, so I'm going to switch to an external flow. We're going to have heat conduction in the copper tubing, so I'm going to turn on heat conduction in solids. And we want a little bit of the air to rise as it gets hot, so we're going to turn on gravity. Now we're going to define our fluids for the study. In this case, we have two fluids, so I'm going to turn on air for the primary, which is going to be the first one that I select. And then under liquids, I'm going to go grab water, and that's going to be what's in our tube. And here we're going to make sure that default fluid is set for the air. Now, because we did select that we're going to have heat conduction in solids, it's also going to ask us for our material. I'm going to set the default material is going to be copper, and that'll define copper for everything. Then here we're going to have the initial conditions of anything. Here's where we're going to set up what our initial conditions of the air is going to be that's going to flow over it. Now, if we remember from the problem statement, our air is going to be at 35 degrees, and it's going to be flowing at 10 inches per second. And we're going to make sure that it's in the Z direction, the direction that we want, so it's going to flow across the pipe, so that looks all good. So I'm going to hit finish. It's going to create our study, and the first thing you're going to notice is this cube sitting around the study. Now that cube specifically is our computational domain, and that is, for any external flow, it's going to create a very large computational domain as it wants to see the flow over it. And it does it a lot larger just so that you make sure that the conditions kind of stabilize. But in our case, we don't need it to be quite so big, so I'm going to bring it down to a size that I found out earlier. So here, the air is going to flow from this side to this side, so we don't really need to have the study thinking too much about the air before the pipe. We need to be thinking more past the pipe, which is why it extends much further this way. Then we're expecting it to rise up a little bit, which is why I put more space on top than I did on bottom. And we don't really expect it to roll over and do too much on the edges, so we pulled it pretty tight on either side. The next tool we're going to use is going to be the component control, and that lets us control which of the components in the assembly are used in the study. Here's where I'm going to do what I mentioned of turning off our two sensor sets of our little discs and our plate behind it. I'm going to turn them off, and Solidworks flow simulation is just going to ignore them. That way the air is going to be able to pass through that plate without thinking that it's hitting a plate, and the water is going to be able to pass over that disc without thinking it's hitting an obstruction. Next, because we have two fluids, I'm going to have to define a fluid subdomain. That just means any enclosed airtight space is going to be recognized. You notice there that I clicked the interior there, so it recognized that entire space. And I'm going to set it to be a liquid of our water. So it's now going to think that anything within that volume is going to be water instead of the air that's default for the rest of the study. Now another thing is, we do not want heat conduction through these little lids, so I'm actually going to put in an additional solid material of a insulator material. I'm going to define both of these two objects to be that insulator. That way our simulation is not corrupted by inaccurate results as heat tries to exchange out the backside. Next, we're going to set up our boundary conditions, and these are kind of one of the two big bread and butters of flow sims. So the first big thing is we need this to be an outlet, and we want to make sure that it's the interior surface, the surface that it's actually coming out of. You don't want to grab the outside, you want to grab the actual inside of what the fluid is coming out of. So I'm going to define that face. I'm going to set a flow opening, and in this case we're going to do a velocity because our flow rate was defined in what the speed of the fluid was. And here we're going to set it to normal to that face, and we're going to set it to 0.1 inches per second, which is what we were given, is the speed of the fluid in the pipe. And we're also going to change the temperature of it to our 150 degrees Fahrenheit. So now we've got the flow is going to come out the way that we want it to out of that opening, but it's going to flow, run around, and then now we need to set this surface to let the fluid exit. So in this case, the easiest way to set up an exit like that is to select the pressure opening setup and grab just an environmental pressure, and that'll let the solver decide what conditions it needs to put for the flow to kind of balance out at that boundary. So there we now have an inlet and an outlet. So those are our two boundary conditions. Next, the other big bread and butter of FlowSim is the goals, and this is goals or parameters that we want the simulation to try to converge against and make sure that these numbers are stabilized. So we're going to insert some surface goals. First, we're going to set this one, and we're going to make a goal on that surface with the parameter that we choose is going to be the temperature of the fluid. We're going to grab the average temperature, and then I'm going to change the name of it to temperature inlet. We're going to set another goal, this time another surface goal, set it right here on this surface. Once again, a temperature of the fluid average, and this one we're going to call the exit temperature. We're going to create a different type of goal this time. This time we're going to do an equation goal, and this lets us set up an equation of other goals. In this case, I'm going to take the inlet fluid, hit the minus key, and the exit fluid. That's going to subtract the exit fluid from the inlet fluid, which is going to give us our temperature drop. I'm then going to change this to be the temperature drop, is going to be the name of it. And that's going to calculate for us what the difference in the temperature is. I'm also going to put in one more parameter of a surface goal on the outside of the pipe. And this one we're going to set to a maximum temperature of the total temperature. And that's going to tell us what the max temperature of the pipe is going to get. That way we can tell if the temp is going to get too hot. Maybe we're concerned about too much heat going into the system and it's going to melt the pipe or something. So now that we've set up a few good goals that we want the study to converge around, we're happy with that. And the final step is just the meshing. Now the way that FlowSim does its meshing is it'll fill this boundary, the domain with small cubes, and then it can further subdivide each of those cubes into smaller chunks, into 8 smaller cubes, and then each one of those it can subdivide. And what we're going to decide, or what we're going to set, is how many levels of refining it's allowed to do. Now globally we're going to set it to 2 levels. And I'm also going to change the aspect ratio, and that's going to say not all of the cubes have to be the same size. And this is the ratio of how much the smallest to biggest one is. And it's going to focus that size change around the geometry in the model. But we also want a local mesh. I'm going to turn off the fine local meshing. We're going to put a local mesh on the interior surfaces and the exterior surfaces of our pipe. And we're going to tell it that at any boundary between a solid and a liquid, we want it to refine the mesh an additional 2 levels. And that way we know that our interactions at those boundaries are going to be running well, and just making sure that nothing gets absorbed into a over-averaged region. So I want to check the mesh, so I'm going to run the study, and it's going to pull up the run dialog box, and I'm going to turn off the solve so that just the meshing is turned on, and that'll run the solver and just run the solver to create the mesh. So here I'm going to click over to the solver, which runs as a separate program. We'll see at the bottom here we've got a progress bar as it's thinking through meshing the model. The 2 default dialog boxes that pop up is the info and the log. The info tells you some information about what's going on in the model, how much CPU process is happening and what the calculation times. It's also going to tell you any warnings like, oh, we've melted a material, or a fluid went turbulent, or a fluid went above its Mach number, so it's going at supersonic speeds. Over in the log, we're going to see anything like how long the whole study went, what's the average time of each iteration. And now we see down here at the bottom, the progress bar says that it's done. So we're going to close out of the solver. Now we have some mesh results have been created, but it's only the mesh. So I'm going to hit expand, and we have some features to analyze our results. I'm going to insert a cut plane, and you see we're going to do it on the front plane, which is the plane that bisects all the tubing. And I'm going to set it, the parameter we're going to display is the mesh. So here we see our mesh. Here you can kind of visualize the squares and what I was saying of the refinement. So this is the largest square to the smallest square. That's the aspect ratio. And then this square to this one is subdivided. Then this one is subdivided an additional time. And you see the 1, 2, 3, the levels of refinement that we selected. So this mesh looks pretty good. It's tight enough wherever we need it to have increased accuracy. So I'm gonna hide that, and then we're gonna run the study. And this time we are gonna tell it the solver needs to be on. It's gonna be a new calculation, and we could select if we wanted to how many cores we want the simulation to run on, or if we want to export it to a different computer. Maybe you have a big thinking computer that you want to use instead of your personal workstation. So here we're going to step back over. Now, as it's going to prep the model, and then we're going to be able to watch it as it actually runs through the iterations. As soon as it finishes prepping the model, it's going to pop up a few little visualizations, but I'll explain those to you. So first off, while it's calculating, we're going to want to see how the goals are working, because it's focusing its solving on refining these goals. And here we see the goals. They're color coded, and we're just seeing the value of them. Because they're all the same parameter, it's going to show us the actual numbers of what each one's temperature is. If it was different parameters, so maybe you have one that's speed and one that's temperature, it's going to just show you 0 through 1 level of refinement. So what the solver is trying to do is trying to find a case where within this bounding region, the actual numbers have converged to a flat line. So we know that that is a converged state of the simulation. The solver actually finished. So I'm going to close this. So now you see, now that we've run a full study, we have a lot more results to be able to skim through. I'm going to put in a quick cut plot, and I'm going to tell it to do a heat map, and the parameter that I want to look at is our temperature. So our temperature goes from 150 to our lowest temperature. I'm actually going to change the temperature to 100 degrees. That's because we want to make sure that the water is at least getting below 100 degrees, and it looks like it does. It gets below the red. It's getting at least into the yellow, which is something below 85 degrees. I'm pretty happy with that. I'm going to put in an additional cut plot, and this time we're going to put it on a right plane so we can see what the air is looking like. I'm going to put this 5 inches out, which is kind of about in the middle, and here we see that the air is flowing in this direction. It's getting heated slightly, and then it's rising up slightly. So that's about what we expect the fluid to look like. So the cut plots are pretty successful. Next, I'm going to show you all the actual trajectory of the air that's passing over it, which is why I put in this back plate. I'm going to say along this plate, I want 1,000 entities to be generated of sphere sizes, and that's going to create little spheres that will follow along the path of the fluid, and we can color it along what the temperature should be. So here, this is a post process, so it's going to think for a second as it puts those spheres along the flow. So here we can kind of see how the water does flow. We see a little bit of coloration as some of them are getting heated up. Now the nicest part about this is I can actually play this as an animation. I'm going to slow it down some, but you see that it's actually animating where the air is flowing. So this is a great thing if you want to do a final animation for your boss. You can show them exactly how the air flows over the copper pipe. And we see it does go up a little bit. It does rise some. So our heat rising looks to be about accurate. So that result parameter looks pretty good. Now that we've kind of confirmed that everything looks good, we want to get some actual numbers. So I'm going to turn on a goal plot, and this will let us see the actual numbers for those goals. So I'm going to show that, and here we see the inlet and the outlet temperature. Here's the numbers of those. It passes by the exit of the first fitting at 145 degrees, and it goes into the exit fitting at 83 degrees for a temperature drop of 62 degrees. And our maximum pipe temperature is 140 degrees, but the main thing is our exit temperature is below the 100 degrees we were looking for, so it looks like our simulation is indeed successful. I'm glad that y'all were able to join me.